a lot of slides here, okay? But it's a cool topic, and it'll move pretty fast, okay? So for benchmarking. So we're going to do a quick recap of weights, and then do a deep dive into the benchmarking process inside of Frame, okay? So first, we said this already, and we will say it over and over again, that blockchains are extremely limited environments, right? You can really treat them kind of like these embedded systems, right? They have very limited execution time, which is, equivalent to the block time. Very limited storage. I mean, not actually limited in the context of like, being limited, but it's very costly, right? The storage inside of the blockchain needs to be duplicated on many, many nodes across the world, right? So when you access 1 megabyte, it's actually putting hundreds of, maybe thousands of megabytes of data out into the world, right? Memory bandwidths are limited. Network bandwidths are limited. It's a very, very constrained environment. And there are trade-offs for, that you can make when you're building a blockchain. There's trade-offs between performance and centralization, right? So in general, in a blockchain system, nodes are expected to be decentralized and distributed, right? You can, of course, increase the requirements of the nodes running your blockchain, but by doing so, you're basically leading to like forms of centralization, right? And I think that this is a scaling solution for some blockchains out there. I mean, if I had to call it out, like Solana, I think is known for having very, very, very expensive validator hardware. Now, this is a trade-off that they are making, right? Not everyone in the world can access that level of hardware, right? That being said, people can, and they can still have some kind of level of distribution and decentralization. That's their decision, right? But I think in Polkadot, our philosophy is very much we want to keep hardware at a very reasonable entry level. I think it was described to me when we were first thinking about the hardware was like basically imagine someone who's building a gaming computer. Like that's something that's pretty accessible, not to literally everyone, but in terms of like publicly accessible hardware, right? And that's the kind of hardware we want to run for our systems. So why do we need benchmarking? So again, there's a whole thing that when you're building a blockchain system, even if you're building a blockchain using Substrate, right, you have to make a decision at some point what kind of hardware you want to use. So benchmarking basically ensures that when users interact with our blockchain, that they are not using resources beyond what is available or expected to be able to be used on the network, okay? And then what is weight? Weight is a very general concept used to track the consumption of limited blockchain resources, okay? And that's the whole kind of the main actors in our story today. So what is weight in Substrate? So you can search in Substrate, struct weight, and you'll find this. And so weight is a two-dimensional object right now with two different weight fields. The one is ref time, which is the execution time it takes to run some code on reference hardware. The other one is proof size. This is the size of the data required to create a Merkle proof for the data being used in that block. When weight was originally created, it did not have this proof size limit. This proof size limit only came up when we started building Polkadot, when we started building Parachain specifically. And it could be that we extend weight even more, right? As I mentioned, right now, it doesn't take into account memory, for example, or it doesn't take into account many other resources you can imagine, maybe network bandwidth, right? So it could be that weight could get expanded. But at the high level idea, weight is just these two things. But you should know that weight is basically a measurement of limited resources on the blockchain, okay? So in your mind, it could be any number of dimensions. Weight limits are specific to each blockchain network and the decisions they make about that blockchain network. So notice with the reference time, it is the amount of computation available on a reference computer. When you're building a blockchain network, you must tell your community this is the expected hardware to run, right? Because 1 second of computation on my MacBook Air is not the same as 1 second of computation on my main MacBook Pro or on a server hardware on any different machine, right? All those machines have different speeds, different trade-offs. I mean, depending on the CPU architecture, memory architecture, the database or the low-level storage they use, whatever, there will be different speeds. So 1 second of compute on different computers allows for different computation. Weights on your blockchain can evolve. It could be also that as time goes on, the weights we have today, the decisions for what 1 second of compute is today, could evolve over time, right? In 100 years, computers are going to be way more powerful. Weights should also adapt and evolve to that, right? In general, again, as I mentioned, the more requirements you have on your hardware, the more performant your blockchain can be, literally in transactions per second, right? But it also limits participation of validators. It limits how expensive it is to run those machines, how accessible those machines are, right? And then again, these proof size limitations is something relevant for parachains, but mostly ignored for solo chains. So if you're building a solo chain using Substrate, you don't need to worry about proof size stuff because you're not actually sending Merkle proofs around the network, right? You're just maintaining your own database. For parachains, and we'll learn about this in the next section of the academy with Polkadot, that we actually send Merkle proofs over to the relay chain to actually do validation function, okay? And that's what that POV was, the proof of validity. That's kind of what that is there. But yeah, one thing I want to also mention here, as an aside, whenever you hear anything about transaction per second, about any blockchain, it's a signal of bullshit or marketing. That with the information you have so far and you know, TPS is absolutely related to many decisions. Some of them are architecture, some of them are the how well the software is designed, but a lot of it is related to just hardware. Like I could take the exact same Polkadot code base and I could make it match any number of TPS that you want. If you want 1 or if you want 1,000,000, I'll just increase my hardware requirements. I'll decrease the decentralization features or many other other things that we try to keep around to make these blockchains resilient and actually useful, right? So these TPS numbers, in most cases, are just total bullshit and marketing. Another way to approach this thought, in my mind, there are opportunities for revolutionary changes to software, to algorithms, whatever. That aside, we all live in the same physical world, right? There is a physical computer doing passing physical packets across physical networks across the world, and all of these things happening, right? So if someone says, I somehow am doing 1,000 times more work than you, right? There's only two real options here, right? They've either made a brand new, innovative thing which is going to revolutionize the world, and everyone's going to get that 1,000 times performance increase, or they've made compromises or cheats that are basically lying to you about what their blockchain is actually doing. Does that make sense from my perspective? Again, there are trade-offs. There are plenty of software and hardware trade-offs you can make to increase and change TPS. But practically speaking, everyone in the world is living and working in the same world. It is not that someone can really achieve order of magnitude difference without any compromise. It's all decisions. And actually, my first presentation for you in Polkadot will be the decisions of Polkadot. So that's really the mindset to have in terms of hardware, okay? So what can affect relative weight? Processor, memory, hard drive, operating system, drivers, even the Rust compiler can affect it, right? There are optimizations happening to Rust compiler all the time, right? Runtime execution engine, right? Which interpreter we're using, the database you're using, the Merkle tree format, so much more, right? So all of these decisions can affect your weight. So let's take a look at what a weight or block weight kind of looks like. Break it down, right? So in Polkadot, at least, we have 6-second blocks, right? So every block, you have 6 seconds to do the stuff you need. What we actually do is the 6-second block is broken down to 2 seconds for execution, 2 seconds for network propagation, 2 seconds for block import, right? So in 6 seconds, not only do I have to be able to do my computation, I have to be able to send it to everyone else on the network, and they have to be able to execute my code as well. So for a 6-second iteration. So when you're actually building your code or your execution, you're only getting a small window of the 6 seconds, the 2 seconds here, to actually run your stuff. And then in that 2-second window, there's all these different parts, right? We talked about the block import, some additional block import, but also on initialize, any extrinsics on finalize, stuff like that, right? I think this should actually be like block initialization, not block import overhead. That's managed over there. But then also, you have within the extrinsics, each extrinsic has its own breakdown as well. There's a base level cost for just dispatching an extrinsic, right? There's the extrinsic itself, its logic, right? So actually inside of Substrate, you keep track of like how much the base cost of an extrinsic is without any logic, the lowest cost of an extrinsic. And then custom weight for the extrinsic logic that you actually want to run. And all of this has to fit in with the on-initialize, on-finalize, all extrinsics have to fit into this 2-second window. And that's what weights help us do. Yeah, you have a question in the back. Can we get the microphone? I think there's one right here. Which chuck it. It's okay. It's good.
The extrinsic. So the extrinsic is the logic. The base. What was it again?
Extrinsic base is basically the there is some non-zero overhead just dispatching an extrinsic, like accepting it, doing signature verification, whatever. So imagine that the smallest extrinsic you can make is remark, right? Remark has no logic in it. It's just accept it, go. So in that case, the cost of remark extrinsic is just the base. But if you add like a for loop, if you add a storage read, if you add this and that, all of this is increasing the extrinsic cost.
Question. Are the 2 seconds and 4 seconds, they're just arbitrary for the example, or are they concrete?
This is literally what's in Polkadot, but you as a runtime developer can actually adjust how much you want. So if you're making a blockchain which has higher networking capabilities or like higher networking expectations, you could maybe increase the available time and decrease the buffer, right?
Okay, and back to the extrinsic base, is that something that we define? Because
this is all being given to you when you let me explain. So, but that's all benchmarking. So we have a benchmarking pipeline which calculates all these numbers for you on the hardware you want, and automatically. That's the magic thing is like you can decide I want everyone to use a MacBook Pro, and you can run the benchmarks on your MacBook Pro, and all these numbers are generated for you automatically.
okay,
Except for you have to write benchmarks for your extrinsics. So we'll talk about that. So that's the process. All right, let's go.
But the ratios are not coming from the weights, right?
The
Like
ratios. This
is
top
just
ratio.
the division of like the units of measurement, right? Like it measures this, it measures that.
The units of measurement are literally
No,
seconds
I don't
and
mean the
bytes.
units of measure. I mean what is measured. Like
What?
so these are the things that are being measured. So we have a measure for this.
Yes,
and a measure for that.
yes, exactly. We measure.
Okay.
We have a measure for all these things.
Okay.
Exactly. And I'm not including other stuff here. There's other hooks. There's like on idle. There's this and that. Like I'm just giving you an idea that there's some execution time window you have. We actually measure everything in it to make sure it's safe. Okay. Okay. So this leads us to the benchmarking framework. The question we're already getting to is how are we going to measure these things, right? And for this, we have created a framework for benchmarking to actually measure these different things and make sure it all fits. So what's the plan? The benchmarking plan. What we want to do is basically use empirical measurements, literal measurements of the runtime executing to figure out the time and space it takes to execute the extrinsics and other runtime logic, okay? We will run benchmarks using a worst case scenario condition, right? We use worst case scenario because these blockchain systems need to be resilient to attack. It is not helpful if in your optimized best case scenario blockchain, you can parallelize transactions and do this and do that, that is not a resilient, useful blockchain. You have built a extremely optimized, like easy to fail computer. Like when blockchains have in the past have histories of going down, it's probably because they are making so many optimizations, so many assumptions, they're not actually able to handle real attacks. For Polkadot, that is not acceptable. We are measuring things in the worst case scenario with our primary goal of keeping the runtime safe, to keep the blockchain up and going in the worst case scenarios. The secondary goal, after keeping the runtime safe, is to be as performant as possible, right? But it is not going to sacrifice performance in order to optimize things, in order to make our runtime unsafe. We will optimize first, keeping our runtime safe, okay? And that sometimes means having some overhead. That's not great. So, just like all of other frame, we use macros to help you with this process. And what I want to get away with here is that creating benchmarks is very similar to creating tests. That's why we have these lectures back to back. That when we actually go to create benchmarks, it's basically like writing tests in the worst case scenario and then letting the benchmark system measure the cost of running that test. Okay? So you can see here there's a module benchmark. We make functions called benchmarks. We do some code that we want to write. We call our extrinsic and we mark that point in the benchmark. This is what's actually getting measured. And then we can even write additional logic which verifies the benchmark ran as expected, right? But we're ultimately, with this extrinsic call on the name, we're measuring the cost of this extrinsic given this setup. And and not including the verification, but allowing us to verify that the extrinsic ran as expected, right? Very much like a test. So, inside of the benchmarking system, we measure many times our benchmarks. It runs you configurably. It can run any number of times, and then we do linear regression analysis. So basically, one of the requirements inside of benchmarking and substrate is that we require that no extrinsic has more than superlinear complexity. So you cannot create functions inside of the benchmarking system that would scale more than O of n. And so when you're designing your blockchain extrinsics, you must make sure that they do not scale more than O of n. Okay, this is important. And this is generally important for scaling a function, right? Like, these functions are callable by the external world. If they can make your function execute O of n squared, n log n, whatever kind of higher order operations, that's a pathway to attack. They're going to get exponential advantage over your function and over your blockchain by increasing that n, right? We use ordinary least squared regression to be able to create these linear lines, and we support multiple linear coefficients. So when we're benchmarking a function, your function may be dependent, or the complexity of your function may be dependent on multiple different factors, right? Like how many people voting, how many total users, how many this and that, etc., etc., etc. We support, of course, doing a linear regression fit with a formula that has any number of coefficients. Okay, and we'll see this more in example. Okay, and of course, anytime we use a constant time function, so where there is no linear fit, we'll just do the median value, not the mean value, the median value. Okay. So to help you with all this stuff, we've also created the benchmark CLI. And so this is what I mean when you can just run all this stuff on your computer and immediately get the benchmarks. So when you compile your node with the features runtime benchmark, you will get access to the CLI. And you can see here there's a bunch of different benchmarks we can run. So there's the palette benchmarks. These will actually run the benchmarks that you write. But there's also benchmarks for storage. So if you want to just detect how performant the storage operations are with the database you're using and the underlying hardware you're using, you can do that. The overhead, so this is the per block and per extrinsic overhead. So we actually measure for you automatically how much that overhead is, right? We talked about that per block, per extrinsic. A command to benchmark the hardware. So we run general hardware benchmarks just to see sanity check. So like, imagine you're launching a blockchain. Someone comes to you saying, hey, I have some hardware that I think is the same, but the weights are way worse. You ask them, please benchmark your machine. Tell me what the outputs are. We're doing very general hardware benchmarks, and then extrinsics as well, right? So all of this are tools available for you to benchmark your hardware. Yeah, I think the difference between palette and extrinsic, this is, you can call a benchmark on one extrinsic, or if you call palette, you call the benchmark for all of its extrinsic. So this is the opportunity. Yeah, question.
Is there any frame of reference for like what numbers are good, what numbers are bad?
Right. So we, in the Polkadot ecosystem, we do have a reference hardware. If you go to our docs, it talks about it. It's like a i7, this, whatever, with an NVMe drive, etc. And then all of Polkadot has benchmarks which you can compare to, right? So you can see, like I can tell you right now, like we can look up the weight of a transfer. So if you're building a new blockchain with a new hardware, whatever, you can compare our transfer with your transfer, right? At a high level.
So just so I understand, like basically what we're doing is we're saying I expect this, like my frame, my palette, to be able to be run minimum on a given machine.
So no. So take a step back. So there's palette development. I'm writing code, and I am writing also benchmarks, so you can benchmark my code.
Yeah.
Now, none of this is assuming the hardware.
Okay,
it's just general benchmarks. At some point, you're launching a blockchain network, right? At some point, you're telling the world, run this hardware. You can't tell them, you're going to run on a Raspberry Pi, and I'm going to run a MacBook Pro. These two computers are not the same. So when I launch my network, I'm telling them, hey, everyone, I recommend you run on this hardware, whatever, or you're going to have performance hits. And usually performance hits are coming from validators, and validators which don't build blocks lose money.
But you also mentioned like earlier that like if people have like really strong machines, then they can have unequal power, right?
Right, but that's the thing. So we don't care if you build your if you have a 2-second block. We don't care that you built your block in 0.1 second. What we care is that the rest of the network is able to input your block in 2 seconds, right? Like you can run really expensive hardware. That's advantageous for you for whatever reason. But we want to make sure is that the whole network doesn't start lagging behind because you are so strong, right?
Okay, so then
So so the benchmarks are at the level of the average hardware,
the average or minimum?
the minimum hardware.
Yeah. Okay. So you're saying like here's a palette. It
Yeah.
can by benchmarking you're saying I can guarantee that it will run at on minimum with these minimum requirements
At this speed, exactly. That is, what you said there is exactly correct. Okay. So there's the palette subcommand. You can benchmark. So just going back to this, these commands here, there's a palette subcommand, which is the most relevant for us. You can benchmark all the weights of functions within a palette. Any arbitrary code can be benchmarked. So you could write a benchmark inside of your palette, which is just like, count to 100. Like it doesn't have to be an extrinsic. You can write whatever you want. And then this palette subcommand automatically generates weight files for you. So actually, if we go really quick into Polkadot SDK, if I pick up any palette, if I go to substrate, frame, let's go balances. I like balances. Balances. There will be a weights file, which is auto-generated. Where does it say? This is auto-generated weights file. It tells you a bunch of stuff like what when it was generated, what inputs were, what CPU and stuff you're using, right? And it generates for you this weight info trait, which is a trait which allows you to access the weight of every extrinsic in your palette, and it returns here hard-coded numbers, which are telling you basically the weight of that call, right? It's all happening in here, and this all happens automatically for you. So let's go back to the thing. So you can see here, there's a trait generated for you, weight info, which lists all of your extrinsics that you have benchmarks for, and then you can use them in your palette. So right now, all of your palettes have the weight as default, right? You can imagine just pointing to this function, and it will return the weight for that function. And also remember, we talked about it in the palette call. We could have that top level weight info, and this would basically map to this, and it would automatically map each extrinsic to the right one. So you only need one line written if you wanted. Okay? So let's walk through the steps of the benchmark. And really, you can do it yourself. You can go to frame benchmarking source librs. There's a function called run benchmark. But I'm going to walk through what the process of running a benchmark is, okay? A lot of steps, but it kind of makes sense. First, we select which component we're going to benchmark. So for each component and repeat. So for each component, like there's a, again, if there's a extrinsic, which is dependent on 3 different factors, those are 3 different components, right? Like let's say number of users, number of locks, number of proposals, right? There's 3 factors for this thing. For each of those components, and for how many repeats of the benchmark we want to run, we will select the component to benchmark. So we'll select users, whatever. We'll generate a range of values to test. So from 0 users to 1,000 users, whatever. We will whitelist any known DB keys. Specifically, like we don't want to include in our benchmark database reads, which are not our responsibility. So it might be, for example, that you need to read the block number. We don't want to measure that the block number read is our cost, because we already know the blockchain reads that number 1,000,000 times. It's already in this overlay cache, right? So we just ignore all the ones that are not our responsibility. We set up the benchmarking state. That means, remember, we had a setup function here, so you can set up the benchmark in whatever way you need to actually succeed. You commit the state to the database, and then we clear the cache. Again, worst case scenario. This is normally when you're running a blockchain, you have plenty of cache. Things are way faster. But in the worst case scenario, you're accessing all database entries the first time. We're always doing worst case scenario. Then we get the system time. We literally call into your computer, what is the current nanosecond time? We execute the extrinsic, and then we get the time again. But this is as simple a benchmark as you can imagine. We just get the time twice in between calling the function. We count the number of database reads and writes we have in our database layer. We can actually keep track of how many database reads and writes we did, and then we record all that data. So the high level, we set up our benchmark, We do it, measuring the time, measuring the database, and then we record the data. And again, we measure database because we know it's such a significant, relevant part of the operation. You could imagine if we want to extend this, we might even want to measure memory. I don't know how we measure networking on a single computer, but there's other things you can measure. But these are the main parts, like the logic and the database of your extrinsics. That's the main pieces of time taken.
When you say record data, that means basically like the benchmarking data, which is the time and the DB reads and writes.
Yeah, but there's a lot more metadata too. Like there's each extrinsic name. We have all of the data. Like the raw data has every single extrinsic individually benchmarked, like each loop. And then we take that data and then we do the linear regression fitting, and you get an output with just one number, right?
Okay, I see.
Yeah, but the raw data is like raw data of every single thing that we measure.
The variables there are the time, the execution time, and the
Yeah,
reads and
exactly.
writes.
I will see examples of it. Okay. Okay. So again, let's imagine a function with three components. Again, x, y, and z. These are the different variables which can affect the performance of your function, right? It could be that you have a perfectly constant time function. It could be you have 10 variables, right? But in general, when you're building a function, you need to keep in mind what is the complexity of my function, right? So x, y, and z, we set the number of steps to 3. So this is configurable in the CLI. We can vary each component at a time, selecting the highest value for the others. So when we have exactly the situation, and we set the number of steps to 3, we'll end up with a table like this of benchmarks. So let's explain this table. So x is between 1 and 2. So you see here, x only has values 1 and 2. Y is 0 to 5. 3 steps for 0 and 5 is 0, 2, and 5, right? Those are the 3 places we can split 5. For 10, it's 0, 5, 10. So obviously 1 and 2 can only be split in 2 cases, right? But where we can, as best as we can divide by 3, we divide by 3. 0, 5, 10, 0, 2, 5, 1, 2, okay? And then in the situation, we measure x at 1 and x at 2. Those are the 2 steps for x. And we measure the other 2 in the worst case scenario. We measure x at 1, 5, and 10. X at 2, 5, and 10. And then we do the other one. So now we're measuring y. Y will be 0, 2, and 5. We measure 0 at 2 and 10, the worst case. 2 at 2 and 10, the worst case. And 5 at 2 and 10, the worst case, right? So we only need to run the max case one time. You see, we're kind of optimizing the table. And same with this one. So you can imagine, again, given these inputs, given these steps, we can generate this table. And this table are the number of times we'll run benchmarks and we'll input to our benchmark function.
And given like a parameters that are like a struct, then it will
No,
just
no. So
flat them.
with structs, you have to turn them into something that is
Yeah,
just a
it
number.
will flatten them.
You have to flatten them. You have to figure out some way that works, right? Yeah. But yeah, in this case, x, y, and z have to be U32. They are only U32. They're only linear. So somehow you have to, in your benchmarking, map those numbers to whatever you want to generate. Okay? Then we take that table. Each line is a set of inputs into our benchmark. Our benchmark has, like A, X, B, Y, C, Z plus K. And then we create linear regression fit for each of the different components, right? So we're only varying one component at a time and measuring the other 2 fixed, right? So in this case, where there's 3 components, we have 3 graphs, right? And the slope of these 3 graphs will tell us how the constants of these 3 formulas, so we can always know the time. So given this table, we're able to approximate the time of a function given any inputs, right? And again, in the worst case scenario. Yeah, go ahead.
At which point do you recognize that this is not linear? If it's not linear?
So when you run the benchmark, you can. So hopefully, first this. When you write your code, you should know if it's linear or not. It's not unknown whether you write linear or non-linear code, right? But if you miss it, there is the ability for you to output this the raw data and to graph it. So all of these graphs are being generated using the raw data, And we have tooling in the ecosystem so you can see these graphs. So you'll be able to see your data points going to nonlinear. And I'll show you actually where we caught this problem in our code and where we fixed it. Okay?
Also, you said like we, as in Polkadot. I'm not sure. Like like we did not allow linear regression, right?
The framework does not allow for nonlinear extrinsics because of this benchmarking framework.
Yeah. So that means at what point would that fail? Like if I write now like a nested for loop.
Right. So what will happen will be that we will generate a weight formula which is inaccurate, right? And that either users will be underpaying or overpaying for weights. So imagine that you had some kind of exponential curve, right? Either the linear fit will be over the curve or will be under the curve. But either way, the curve will not predict the actual path.
Okay, but my point is that like there's no like a point that like you cannot deploy this code or you cannot compile it or something doesn't pass.
So we do not have a layer where we detect this isn't linear. I don't know maybe you can do it, but it's like like data points are all over the place. Like if you tell me the linear fit of this numbers, it's going to do it. Like that math will allow any input to a linear fit thing, right? Like another thing, when you're in Excel, they give you a drop down for like which fit you want to do. They don't tell you, oh, this is an exponential fit, right?
I don't know what you mean by fit. I don't use Excel, but
it's a line. Like
yeah. Okay.
Okay, I think this is maybe a conversation for later. You should search about like fitting to data, but
Okay.
normally you need a human to be able to understand what kind of fits into data. Data, it's hard for a computer to know that kind of stuff.
Not going into this too much, but you could check the data points and the distance from the curve in that X, and if it's too distance, then
Right, but
it failed. And
let's show you some real data. It's easier said than done. Okay, but yeah, sure. I mean, if you can think of improvements, like we're happy to accept PRs, right? But it's really like you're thinking a lot of optimal cases when you get a lot of stuff which would make it look weird. Okay. So that's the high level idea for the timing. So one thing we have here is the ability for you, again, this is the palette storage macro. We have the ability for you to add an additional macro on top of certain things called whitelist storage. And these are storage items which are accessed every single block, right? Like the block number, events, total issuance. These storage items, no matter what code is running, will always call these functions, right? And we don't want to count these storage reads into our benchmarking. So we whitelist them, and all of these storage reads are accounted for in the block initialization, right? So when we run the block initialization benchmarks, we will access all these storage items, we'll account for it one time. But then in your benchmarks, we don't account for it. We whitelist them. We ignore them, right? So if you're making a palette, let's say that every single block, the first thing your palette does is read some storage. That means your blockchain will always, every single block, read some storage. You should whitelist it. It will get included one time into the block initialization and not every time into every extrinsic, right? This is the optimization. And we know this is okay because of the overlay layers, right? That once you read it one time, it's in the overlay, and access to that is very cheap. So let's give an example with the identity palette, okay? So in the identity palette, an identity can have a variable number of information, the name, the email, the Twitter. Identity can also be judged by a variable amount of registrars. Finally, an identity can have a two-way link to sub-identities. So other accounts that inherit the identity status. So I'm trying to describe to you, these are the components. These are the variables on which our identity palette can have varying complexity. So let's look at the extrinsic kill identity, okay? Do I walk through the steps? No. Do I walk through the steps? Yeah, so at a high level this, so we have a ensure origin, we look up some information, we take some information, we remove some data from storage, we take another data from storage, we iterate over some data. This is hopefully a bounded loop, right? We iterate over that data. Okay. We iterate over that loop. We then have some hook that actually can hook to some other pallet, and we deposit an event. So let's look. The first thing, the kill identity will only execute if the force origin is calling, right? However, this is configurable by the pallet developer. What origin is actually allowed to call this function is configurable, right? So how do you make a benchmark which can actually benchmark this function in every case? Right? For this, we needed to add special functions behind a feature flag. So when you create a custom origin, you must also implement, with this feature flag runtime benchmarks, a successful origin function. So you need to give us an origin which will succeed in calling this function. So if I have a palette and you configure it so that only a governance call can succeed, you need to hand us, when we run benchmarks, the governance call that would the governance origin that would succeed so that this call would succeed. Right? Does that make sense? Okay. Next is that there could be external logic or hooks. So in this context, again, we have some associated type lookup, which has this function lookup, which is being defined outside of our palette, right? Now, thankfully, our benchmarks will run this code and we'll benchmark this code. It's part of the code path, right? So whatever logic you want to do, we will run that code. But it is important that when someone implements this function, they do so under the information that you provide about what you expect the complexity of this function to be. So when you expose a configuration like lookup in your palette, it can't be that someone implements that they're going to scrape the whole database, find their favorite user with the most balance, and then give it to you. That is an extremely complex function. Lookup in this case should be a very simple constant time lookup to one specific user. Does that make sense? You can imagine when you give the user the ability to write the function that your pallet's going to execute, right? That if they introduce other levels of complexity that you are not expecting in your benchmark, you're not going to be able to benchmark for it. You're not going to be able to know your benchmark needs to run it. So when you make these kinds of hooks available, you need to express, I'm expecting these complexities, and when you write the function, you must implement it with these complexities. Now the question you might ask is, okay, well, what happens if someone doesn't do it right? You get bad benchmarks, you get bad weights, you get bad fees, your blockchain is potentially attackable, right? Okay. So we have some determinate. So in all benchmarks, all storage reads and writes are deterministic, right? Like it's not random what's going to be read. Based on the inputs, you'll have deterministic storage reads and writes. So we go in and we can see that here there's going to be two storage reads and writes. We're both taking, right? So that's both reading the item and then deleting the item. So two reads and writes. And the size of these items will depend on how many registrars there are and how many additional fields there are, right? So we already have complexity that when we're reading this item, the size of that item is going to depend on how many registers there are, right? Or fields. There are also loops where, depending on the inputs of the function, right? We might read or write an item more or less, right? So this is a storage write, which is dependent on our input to our benchmark, right? Yeah. What happens with the slashed funds is configurable too. Oh, this is something some code problem. Whoa. Yeah, I don't know what happened. This is some kind of problem with the rendering of the thing. Okay. Anyway, that's fine. So it makes sense, right? You have some parts of your function, you will always read or write this function, other parts which are dependent on the inputs. And then of course we have whitelisted storage. So when you deposit a new event that something happened, events are always something that's read, always something that's written to. So we're not going to count this into your benchmarking, okay? So writing our benchmarks. We have the three components we want, right? R, S, and X. We need to set up an account with funds. We need to register an identity with additional fields. We need to basically set up all the worst case scenarios for registrars and sub-accounts. And we need to take into account the force origin that will succeed to make the call. Right? So here is what an identity benchmark looks like. We have a function, kill identity. We have R, S, and X, which are linear, which are, I guess, like, linear data points between some initial value and some maximum value. And note that these max values, these are all configurable, right? So when you put into your palette that the user can have up to some constant or some configurable max number of users, this is where we're getting this information from. So when we run the benchmarks, we're running it against a runtime which has a specific configuration, right? And when you increase, like go from 100 to 1,000 max items in the vector, you need to rerun the benchmarks because they have new complexities, right? We have some helper function to add registrars. So we add R registrars. We will then generate a count. We will then generate the origin we need. We do the lookup. We make that we give balance to the user. Any setup we need to do, right? We create identity. Let's see. Do I have step by step? No. Scroll down. We go through, we add sub-accounts, we loop over, like we're basically doing all the setup we need to set up our worst case scenario. And then at some point at the end, we make the extrinsic call. We actually call the function we want to benchmark. We do all the setup, we call the function we want to benchmark, and we have this extrinsic call parameter at the top, right? And we can ensure that at the end, that thing was actually deleted, right? So this is not part of the benchmark. But this ensures that this function not only ran successfully, but actually removed the data that we expected, right? The same idea with tests, right? It's not enough to know that this extrinsic ran successfully, but that the actual output is what you expected.
Assuming there are tests, we don't need that, right? Like, if you have tests, like the purpose of tests is to test the functionality, and the purpose of benchmarks is to benchmark. So
no, I still think you should have this. I still think you should have this because your unit tests are tests for your runtime in your mock. This benchmark runs on the runtime in the actual machine.
okay, so but there's no like, in terms of levels of testing, there's no like integration E to E kind of capability of testing, regardless of benchmarks. Like basically to run it like the same as the benchmark.
No, so unit tests. So this is so I think you're saying so. Unit tests, they're set up using some assumptions about what the data types are. So your unit tests have accounts equal to U32, right?
Yeah.
You can't run those unit tests on the real runtime because the accounts aren't U32. They're a different type, right? But these benchmarks are written, again, this is why we teach it after testing. They're written much more generically. Everything here is still generic. We're still using T.
Yeah.
We haven't actually introduced any concrete types.
Yeah.
It actually makes writing these benchmarks a little bit more complicated. But in general, everything here is generic so that we can actually run a benchmark against the actual runtime.
Actual runtime coming from the machine that it's running on.
The machine that's running, exactly. And so in this case, you still should write basic sanity checks. But it's possible I can't write all the checks that I would be able to do in a unit test because I don't have full control over everything, right? So that's the thing. So you can see here, the benchmark components, right? These linear things basically is describing that these variables will change over the benchmark over some linear range, right? Depending on the setup, right? All of these components have configurable but known at compile time maximum, right? So it needs to be known at compile time what the maximum worst case scenario is, okay? And the runtime logic should enforce these limits. There's some setup logic, right? Adding things, removing things, etc. This is just like writing tests. This is exactly just like writing tests. Reusable setup functions, I recommend in benchmarks, you don't rewrite chunks of code over and over. We actually make helper functions inside the benchmarks to actually set things up more easily, right? Always testing the worst case scenario. So we're always, for example, where R is the thing we're benchmarking, we're always giving them as many R as we can, right? As much sub-registrars or whatever identities we can. And then we, of course, execute and verify the benchmark, right? So I have a basic sanity check. Before the benchmark, it does contain the key. After the benchmark, it doesn't contain the key. So this is just basic sanity check that this benchmark is running. And this is good because it has been times before where you write a benchmark and it wasn't behaving as you expect, but it also did an error. So you just basically get a wrong benchmark, right? And there's nothing in the pipeline can tell you that something went wrong, you know? So that's all good. All right, finally, we wrote our benchmark. It's in our palette. We configure we compile our whole node. We can then run our benchmark using the target file that's created, benchmark palette, and a bunch of commands. Now, normally you don't write this by hand. Normally this is part of your CI pipeline or part of a script or whatever, right? But you control over everything. You have control over the chain you want to run it on, so you have different chain specs, the number of steps, the number of repeats, the palette you want to run, the extrinsics you want to run. So if you want to just do one or you want to do a star, right, all of them. Which WASM executor you want to run, how much memory you want to have available. Usually you need a little bit more memory available inside of a benchmark because we're collecting data alongside running the benchmark. So this is not so scary to add more memory, right? Because we need to store the data somewhere in memory as well. Where we're going to output the file, the RS file, and we even support templates. This is a handlebar template. So handlebar is I think a JavaScript or something in the JavaScript world where you can basically create your own template to control what the output RS file looks like, right? And even attach a header file if you want. So really you have full flexibility to take the data and make it into whatever file you want, right? Question in the back. Can we get a microphone in the back, please?
Yeah. So in terms of steps, for example, you should take into consideration what are your components and which steps make sense, right? For example, because in that table generated, for example, the components are ranging from 0, let's say, to 2, right? Some 0 to 10, right? And the steps you input is 50. It doesn't make sense because
no, but that's the thing that you should put a big number, just like 50 or 100, whatever. And when we generate the table, if it doesn't split into 50, like 3 does not split into 2, so we only pick 2. If you have 0 to 10 and you pick 50, we'll just check all 10.
okay. So if you put larger number than the components range, it will test every
item in the range. So it could be you put step 50, but then we only do 2 choices.
So only 2.
Yeah.
1 and 2 also.
Yeah.
Okay.
You want to pick a number that's large enough sample points over your stuff, right? So even if it's between 0 and 1,000, 50 samples is probably good enough, And you can play with these numbers. Again, it could be that your system is different. You can adjust it. You can verify. And also, as I mentioned here, when we go back to the weights tells you what the inputs were to this function, right? So you can always know when you generate weights what they were using as an input. Okay, so let's look at some raw benchmarking data. Oh, the image is so shitty, right? Okay, well, this is what raw data looks like. And this is why, again, who was saying that, we could just detect something. Like, there are outliers all the time. You're running benchmarks on a machine. Computers just cause outliers. You can see. If you can write a program which detects this, then let's use it.
If you would have like a very large input set,
Yeah.
you could overall get a trend, right? And see and figure out if it's like
I think you should go to the data science community and know that these problems are much harder than what you think that you're saying right now. Okay?
Okay.
But I mean, I'm happy to accept certain libraries.
I'm not saying it's a binary. It's a yes or no thing, definitely. But you can.
Well,
see
if it's not binary, what do you want? You want to do benchmarking, and then some human says, "Hey, there's some graph." Okay, press yes.
No,
like
no,
all of
I'm
this is
saying
CI pipeline, so it has to
you can
be.
get a degree of variation from the linear.
Right.
The linear regression.
Again, whatever. Like we're all programmers here. Whatever you want to program you can do it, right? So it's all within limits, right? You make assumptions. The more assumptions you make, also it can be bad too, right? Anyway. So we see here, we have a benchmark. This is the kill identity benchmark over the number of registrars. It shouldn't be this bad, the quality. Okay, whatever. And you can see here, we have a bunch, every single sample point, we have a bunch of benchmarks. Some have outliers, some are mostly coupled. They're mostly tight here, right? And I have here in this measurement, these are all the raw values. The minimum value is highlighted in green, so you can see the green value at the bottom. The max value is highlighted in red, so it's all the red points up there. The median and average are these lines coming here. So you can see the median and average are actually quite stable, even though there are outliers, right? It's quite good here. And I think we would all agree and say this is either constant time or very small coefficient, right? Mike.
When it's benchmarking, it runs using WASM file or the
We use
target binary file.
the WASM compiled. But
WASM compile.
you can configure it. You can configure it. So you can pick which one you want, but it's not running the binary file. It's running WASM.
Okay.
Yeah. So
And-
we need to run WASM. Worst case scenario.
Okay, and also this is per validator node wise. These commands are run.
Not per validator. This is run by like Parity Technologies, and then is integrated in the runtime. The thing is, it's not like each node has their own weights. The runtime has weights which are measured and are accurate for a certain hardware. So when you run the blockchain, if you're running a lower hardware or higher hardware, it doesn't matter that we assume these weights.
Okay, the palettes we write in the parachains, not the frame palettes, our custom palettes, we will need to benchmark that as well.
Yes.
So that will be done by us.
You
not
need
by
to write
Parity.
benchmarks.
Yeah.
Yeah, but then if Polkadot includes your palette in the Polkadot runtime, then Polkadot will benchmark
Okay.
and include those benchmarks in the runtime. They are the benchmark weights are included as in the runtime file, which is distributed to the world
Okay.
in the WASM. The WASM has all the weights.
Makes sense. Thank you.
Okay, let's keep going. More graphs. So here is the other benchmark: extrinsic time versus number of sub accounts. So here, very clear linear increase, right? And then additional fields, again, very clear kind of constant or very slight increase, right? Yeah, this is pretty much just constant, right? Yeah. And here's database operations. So database operations, what am I showing here? I'm showing for sub accounts. You can see the number of reads are in blue, so that's constant. Number of write repeats are constant. Number of writes is increasing linear. So each of these components can have their own graph, right? Their own coefficient. Mike.
We saw for the time there were like the max, min, etc.
Yeah.
Like so under the hood, like the read and the read repeat and all of those also have these.
No, in this context, database reads are deterministic, right? So the number of times we read or write to data is always deterministic based on the inputs to the function. The time isn't, because time takes a computer. Like the computer gets hot or stalls, whatever. But in this case, we precisely deterministically know how many times you read or write to a thing.
Okay.
So we don't. So actually, as an optimization, we don't actually repeat this thing. We run this one time and we have the data. Running it over and over, we're getting the exact same data. So we only run this one time.
Okay.
Okay. So the final weight. So given all this information, we generate a final weight. First, our weights can actually give you metadata about which storage was read. So when we actually go look, let's go look real quick back at the balances palette. When you want to see a balance transfer, where's transfer? FN transfer. Transfer all. You can see here that only one storage item is read, which is the account receiving the funds. Okay? So we have here this. Let's go to a different one. Let's look at a different palette. Let's pick treasury palette, right? Treasury palette. Oh, wait. FN. Oop. FN spend. You can see here in this benchmark, we are going to be reading storage. We're going to be reading one time asset rate conversion or whatever. We're going to be reading and writing to the spend count. We're going to be writing to the treasury spends, right? And then also the proof data. How big are these values? We're giving you all this metadata. Let's go back. We also write down, if you choose the range of the components, right? What's the range we're actually executing these things on? And we generate a function for you which has these components as inputs with U32, and actually all of these like formulas hard-coded, right? Which will calculate the weight, right? It uses the fixed wait time or the component of the linear function and calculates the final weight, right? These are the results of the benchmark. This is, so here, in this line, this is the coefficient which is multiplied by r. This is the coefficient in front of r for the linear fit. So this is a slope, right? So remember back in our diagram, let's go over these three slopes. I said this one is basically constant. This one is definitely very linear. This one is basically constant. And the actual benchmarks is showing, look, these numbers are very small. This is 153 nanoseconds. So it's like this is picoseconds, right? So it's very, very small, basically constant. That one slope that was real actually has a significant factor here. So these are the slopes of those functions, right? And also the reads and writes, you can see that one of those functions actually affects number of writes. So here we have writes, one write per S, right? So that's that linear growth. So the other two writes are constant. That one is one write per S.
What's the difference between the write and the write repeat in the previous?
So write repeat is this is actually this is only for developer information. So when you write to a storage item, that counts as one write. Write repeat is, are you writing more times to the same storage item? It could be an indicator that you wrote inefficient code. That inside of one extrinsic, you're writing the same thing over and over. Now remember, the overlay means that other writes are cheap, right? But it's still non-zero, and having a really high write repeat could indicate to the user, hey, you actually wrote some inefficient code, maybe. So we give this output, but it's not actually affecting the final benchmark. And of course, we do the exact same process for every single function in a palette. Every single one of these things has a formula. And then finally, once you have all of these things inside of this wait info trait, all these functions are implemented, you can integrate it into your runtime just like this. Palette wait, I access that wait info trait, I call my function, and I use the parameters, the constants in my palette as the input to this function. So the weight of this call is the worst case scenario weight of the whole call function, right? The max possible thing. When I start my function, it is worst case scenario. But at the end of the function, after I've read storage, after I actually have the data I need, I can return weight that was actually used. That's the same thing as the pays no, right? In the example I gave with pays no, you return all the fees. In this case, when I first call this function, there's no way for me to know how many items in storage there are without reading the storage. But reading storage is very expensive. Reading storage, that would be too much overhead to calculate ahead of time. So we charge the worst case scenario, and then we can refund to you after we read the items. It's very cheap. We can refund to you the weight that you didn't use. So at the end of the day, the user only pays the right fee. Okay? Initial weight, worst case scenario, final weight. We actually are just taking advantage, like we're already in the logic of our palette. We're going to read these storage items, right? So we already have them around. We can just get the length of it, get whatever we need, and input it back into the same function and get a new weight and return it. And then the transaction payment palette will automatically find the difference of the two weights and return the fee.
So does the runtime before the dispatch depending on the weights on top of the function, hold these fees and then
Yes.
does
So if, for example, you call a transaction, you might need 5 dot to start with, but then at the end we only use 1 dot. But we need 5 dot because we do not know that you're not doing worst case scenario. Again, we're protecting the blockchain. The primary objective is to protect the blockchain.
Yeah, I'm wondering transfer all function. How will that work? So all the remaining balance of account A has to be transferred to B.
Yes.
But you need. How does it happen?
So, but the thing is, transfer all. A balance transfer is a constant time function. It doesn't matter if you're transferring 1 dot or you're transferring 1,000 dot. It's just a
Okay.
number. You're just changing a number.
Makes sense. So all will be remaining after deducting the transaction fee. Remaining will be transferred.
Ah, yes, that. Yes, yes. So we first take the fee, we transfer everything. Yes.
So there is no chance of any fee refund because that's
Yeah.
constant time.
Yeah.
Got it. Thanks.
And if you were to build a function which expects to kill an account, you shouldn't do fee refund.
Yeah.
Okay.
Thanks.
Okay, and that's my way. Any questions? If not, we'll jump into this next presentation. It's much faster, much less dense, but it's kind of cool. Okay. Any questions about the benchmarking? It makes sense, right? Like you're hardcore just measuring everything. We made the pipeline for you. We ask for you write a function which we can benchmark, and that's it.
I have a question. If you go back, like the function that was being tested was returning a dispatcher result with post info, right?
The ones that are doing refunds use the post info. Yes.
Okay, so it's not about. I see. So
So remember,
can I just see it again?
yeah. So it needs dispatch result post info. So the main thing here is that dispatch result is a well-known type. It can return OK, nothing, OK with the unit type, or dispatch error.
Yeah.
Dispatch result post info has more fields and allows you to put more data in.
Okay, so that would be like the weight of this
Mhm.
call, right?
Maybe let's just look at it real quick.
Yeah.
Let's look at it. Polkadot struct dispatch result with dispatch result with info. Oh, post info, right? Is it enum? What do you think it is? Enum struct type.
I guess my question is
Type.
like, do we like manually take the output of the benchmarking and put it like that in the return of the function, or is it
So
when
the
we
output-
annotate it with?
The output of benchmarking is this weights file.
Yeah.
And this weights file is just a bunch of formulas calculating math.
Yeah.
And then we call these functions. It's giving us a number. There's one number comes out, right?
Yeah. So, but we use that in that return type, or do we put it in this annotation? Because there's also the annotation weights.
The return type is weight in that context. Give me a second.
I
Just
think
struct
it was in my phone.
type. It's enum.
But
no,
like
this type.
when we have our calls, like
Type.
in the palette,
Dispatch with post info. Wait, am I crazy? Did I just go? It is enum. Post dispatch info. Here, this. I think I want this struct. It has to be a struct. Enum doesn't make sense to me. Yeah, struct. So here, the thing you get additional with the post dispatch info is two things: the actual weight, which is an option of weight, and pays fee. Yes or no? That's it. So when we return that additional weight, it's fitting into here, and it's letting the calculator calculate. This is the actual weight used.
can you show us how it ties into like our palette development,
Palette development.
like what we're doing now, our assignment basically?
So I do not expect benchmarking in your assignment.
Okay, I see.
But if you were building a palette and you wanted to refund weight, at the end of your palette, so at the beginning of your palette, you put this thing with all the worst case scenarios. You're calling the function that was generated by the benchmarking with all the worst case scenarios. And at the end of your palette, you call the same exact function, but now with the real inputs. And that's it.
I see. Okay.
That's basically it. It's actually quite simple. Another thing you can do. So I don't know if I say this in my my lecture, but I'll say this. Imagine that you have a function which can have multiple different routes. Actually, I have this in the exercise. So, but I'll say it right now. Imagine you have a palette with extrinsic with multiple different routes, right? So it can end condition A and condition B and condition C. Those are all valid, right? So one condition, it creates a proposal. One condition, it adds a vote. The other condition, it closes it, right? All from one entry point. You calculate the weight of all of them, worst case scenario. You put that as the first weight, the worst case scenario of them, and then depending on which output you exit on, you return the correct weight. But anyway, we will do this in the exercise today. Okay. So we'll do the exercise after the next lecture, after this quick lecture, okay? It's be very fast, I believe. So what I wanted to do in this next section is just talk about some of our learnings. Talk about databases, talk about our learnings through the development of benchmarking, and best practices and common patterns, okay? So first, databases. When we started building Substrate, we were using RocksDB. So RocksDB, oh, by the way, I'm not a database guy, so I'm just kind of, I'm reading to you the best of my understanding, okay? But we use RocksDB. This is a database built by Facebook, I believe. And it's very performant and good. It's built in Rust. It scales. It has an infinite number of configurations you can do to make it better. As I understand, big companies that use RocksDB have a single or more engineer dedicated to just configuring RocksDB. Like it's just so extensible or whatever. It's that. It's great for a general database. It supports arbitrary key and value things, but it's a big project. Can be hard to configure properly. We have created, since the initial creation of Substrate, ParityDB, and we use it now. ParityDB is a embedded, persistent key value store optimized for blockchain applications. Just like RocksDB, keys and values are arbitrary bytes, but it is designed for more efficiently storing Patricia-Merkle trees. So in a Patricia-Merkle tree, most of the keys are fixed size, right? They're mostly hashes, right? They're mostly small values. When you're building a Merkle tree, the data is here. Those are big, but there's like a million nodes to get to them, which are all small hashes, right? So it's really optimized for small nodes, right? And a uniform distribution of data. It is optimized for read performance as well. So it's also optimized for reading data, right? Because writing data, we can always do that kind of asynchronously. We can always kind of push that down the road, okay? So ParityDB uses a probing hash table, as opposed to a long structured merge or LSM tree, which is the most common, I think, design for a lot of the most common databases you've seen here. Like this is SQLite, RocksDB, LevelDB, Apache, etc. Because we do not require key ordering or iteration for the tree operations. This means read performance can be constant time in a hash table versus O log n in a LSM. So we're optimizing for reads. I think that I'm showing an example here. So what does that look like? We have in ParityDB this fixed size value table is a collection of 256 values ranging in how many bytes that items will store, and items in that table will always be between the bytes of the two tables. So if we want to find an item that is 1 kilobyte, it will live here between, or I guess it will live exactly here at 1 kilobyte. But if we want to find something that's like 11 kilobytes or 1.1 kilobytes, it will live in this table because it is the closest table that fits the items there. So we can always find an item in the table very efficiently. So the last 256 value table size stores entries that are over 32 kilobytes split into multiple parts. So if we have an item, so this is the last table here, 32 kilobytes. If we have an item that's bigger than 32 kilobytes, we will split that data over multiple chunks and then put it in the table. Okay? Let's see an example. Not an example. I'm going to show some graphs here, but at a high level, this is the idea. This is the optimization we've made for reading data. So more than 99% of the tree nodes are less than 32 kilobytes in size. So when we're designing for a blockchain database, most of the items in our database are going to be very small. Definitely smaller than 32 kilobytes, right? Small values only require 2 reads. 1 read for the index and 1 value table lookup. So it's very fast and constant time to fetch a value. Values over 32 kilobytes may require multiple value table reads, but these are rare. Again, because there's so few of them, you might have to do multiple reads, but it's very rare. This helps also minimize unused disk space. For example, if you store a 670 byte value, it won't fit into 662 bucket, but it will fit into 680 bucket. And so you're only wasting 10 bytes of space. So the uniformity of this table is meant to basically optimize so that you're not wasting so many bytes per section. So you might notice that the table starts very small in the increment, but then starts growing bigger and bigger and faster, right? Because the relative amount of wasted space is still small, right? Does it make sense what I just said? Yeah. Okay. Yeah. Question.
Okay, I think I'm trying to make sense of this long array. So essentially, you know that it's a next column because you know the total size of a row, correct?
Sure.
Is that how it is?
What's a row? What's a row?
Sorry. So you have an array here, but I think you're calling it per column, right? So is this an entire column, or you're saying that this entire array is chunked?
This is a descriptor of the buckets that we put data in this in the database. So there are 256 buckets, and each bucket allows items in it which are which are less than its size and bigger than the next bucket lower, right? So if you have, okay, I want to store an 8 kilobyte file in your thing, we find the right bucket, we put it there. And that means that when you want to retrieve that item, we only really need 2 reads. We look up the index and then the actual value in that bucket. It's very fast to grab that value.
Right. In terms of the optimization, then where is the optimization? Like, do you know beforehand the size of the?
Yeah, that's a good question.
Right.
That unfortunately I don't have the answer to.
Okay.
I think I recommend maybe you can go to the repo, not the actual to read the code, but if you go to Firefox, you go to ParityDB.
I'm very interested in this stuff.
Yeah, I mean, truthfully, I don't know all the details here. I'm not a database engineer. I just want to explain. But this is, he has some details here and stuff that's probably more relatable. Okay.
Thank you. And one more thing, is there so I'm trying to actually understand. Still trying to understand better what kind of data we're storing in there.
So again,
like
so
an example would be great,
yeah. So give me an example. This database lives below the Patricia tree, Merkle tree abstraction. So remember, we talked about 2 kinds of keys. Were you in my substrate storage talk? The frame one?
The first part, yeah.
Yeah, the frame one. Yeah, so there's 2 kinds of keys. There is a key like that key that you walk down the path. This is your tree key, right? And then the tree key leads you to nodes. The nodes actually has the raw data. It'll either tell you go to another part of the database, or will actually have your final here is your account balance. That is what we're storing here. So again, most of the nodes in this database are all just branch nodes. They're just pointing you to other places. They're all small chunks of just pointers. And one out of every 1,000 of these nodes is going to be, here's your account balance. Here is the vote yes or no. Here is the total issuance on the chain. Here is the WASM blob of your code. But most of the nodes getting to that, or most of the database things to get to that, are just pointers in this branch.
Got it. So then, even for a WASM blob, I guess it will grab a bucket that is of its size. It's not like it's sharded or fragmented.
So WASM blob will do this last piece. WASM blob will definitely be over 32 kilobytes. It'll be like a megabyte to 4 megabytes. And what will happen is we will split that WASM blob into 32 kilobytes parts and fit them into this chunk. So we'll split it over multiple parts. And for an item like reading the WASM, reading a 4 megabyte file, it will be much slower. It'll be multiple reads needed.
And just one, last time we were discussing events, you mentioned that we do not query, or we don't want to query for event data, right? So is the event data actually stored in the DB, or is
Yes,
it more
it is.
published?
It's stored in the DB, and it's stored very inefficiently.
Oh, okay. This is just implementation aspects.
Yeah, it's stored in the DB. Everything is stored in the DB.
Thank you.
I don't get, so how 2 reads and not the multiple hops, because you just mentioned that most of the nodes are branch nodes and not leaf nodes, right?
Right. So this is different perspective. It's 2 reads for an item in the raw database. It's many reads from the perspective of a Merkle tree. Right? So it's all about perspective, right? So we can only optimize at the database level. But a Merkle tree will actually have n log n reads, right? It'll be many, many reads, right?
And basically, if you can you bring the previous slide? So all the items that are between 1 and 32 bytes will live like
32 bytes, yes. So the smallest chunk we have is 32 bytes.
Yeah, but we can have multiple items that are 32 bytes, right?
We can have, yeah. This is a there'll be a like a whole bunch of items that are all 32 bytes. This is the bucket. There's a 32 byte bucket.
Oh, it shows like it's like
Yeah.
yeah.
This is not like this is just like an index into how many like tables we have.
Yeah, sure. So my question is, so we are storing the nodes in those buckets, right? And so you said the reads of like two reads like lookup and take the next index, or lookup and take the value. That's only in terms of database, but also like we didn't account the number of hoops. Like after reading the first bucket, if you got the first bucket, it means the node. You have two reads. After that, you go to the next bucket.
Two reads, exactly.
The two reads.
But this two reads is much more efficient than an LSM table. An LSM table might have, just to find your data in the database, have many more reads. So the whole point is that we're optimizing, again, with a Merkle tree, we're reading always a bunch of stuff, right? So we have as optimized as possible at the database level, the read part.
Okay, so in terms, the benchmark also takes into account, for example, the reads, like those two reads, and also the hops.
The way that we benchmark database is we run the database and we throw tons of different data at it and we see its performance. So we don't care how it works under the radar. We are just actually throwing data at the database to store, and we're actually timing how long it takes.
Okay, but in general, in terms of like if you want to kind of like benchmark everything, you take into consideration like you have hopes of going to other nodes, and if you get to that node, you have two reads to find the data or to look up the index.
That's the thing. Our benchmarking is opaque to that information. So like we are not benchmarking at that level of the database. We're benchmarking that there's some database there, and we ask it to store data, and it does something. The implementation detail underneath there, we can't benchmark. It's too low level.
Oh, so okay. So for example, Shawn, you have, let's say, you're reading to 3 nodes, right?
What does 3 nodes mean?
Like you're storing your data, let's say, like.
Say, I am reading your account balance. Okay, then what?
So it means you follow the tree, like the imaginary tree, like, but then.
Yes.
What it means, like you will hop into other buckets of storage.
The problem is this. Going back to so this is the problem. This has been the problem with the last couple questions. Let's go to frame storage. The problem with this conversation is that there are multiple layers for a database, and you're conflating multiple ideas. When I read a storage and account balance, I'm talking from this layer. When I'm saying there's 2 hops to an index in a low-level database, I'm talking this layer. You cannot talk about things end to end here. It's very.
I'm talking about the partial and the key value because it's 1, right?
So Patricia Merkle tree.
And key value, it is 1.
Yeah. So.
Yes.
Let's go this.
Exactly. So what?
So this line is that database read. I'm saying this line has 2 lookups.
Yes.
In the database level.
Yes.
But here to here is 1 hop, right?
Exactly. So for me, I'm saying like for you to kind of like get the whole picture, it's like you have 2 reads and hops to get into that value. Right. So for example, like does the benchmark also take into consideration the hops or only reads?
The benchmark is opaque to this information. The benchmark, it has no knowledge of what's going on in the background. It is just timing things, right? Like imagine I ask you to save some data. I don't care how you save it. I just tell you to tell me the time.
Okay.
It's timing. Like I'm not measuring like literally what bytes are you moving. Like I'm give you some data. I'm timing how long it takes you.
Okay, even the reads and writes are you're just getting and putting that and not
exactly, and I'm just timing it.
Okay.
Right? It's just timing. I mean, that's how you do benchmarking. You don't benchmark at the op level. At every single like operation. Right.
Okay. Can you get the other one with the 32, the column? Yes, this one. So each of these is a bucket, and each bucket will have n data, right? Like whatever.
A ton of
This-
data. Yep.
This ton of data, how do you get it also in one read?
It's not. It's not. I said it's here. It's two
This,
reads.
this is like sharding, right?
It says
Like
two
the-
reads. You need an index read and a. Listen, I don't like the direction of this conversation because, one, I'm not an expert in this topic. I'm sorry, right? But second is like it's like this is very low level implementation of a database. Like I want to show you some of these details because it has impacts on benchmarks. But it's like this is not a academy about building a database. There's actually an entire field of study for building a database engineer, right? So I'm not going to be able to provide to you a satisfactory answer, and I also don't think this is the right context for that. So
Thank you.
okay, let's keep going. Okay. So ParityDB, it exposes synchronous functions, but the underlying write is actually asynchronous. And this is, again, a decision that can be made because we're building a blockchain database. So this is a very common problem. When you have a database, when you're building a database, you want to try to make sure when some computer program says write some data, that it writes that data so that if it crashes, the data isn't lost, right? This is a very common problem in another world. But a blockchain doesn't have this problem because a blockchain has tons of redundant data, has tons of blocks where you can recreate the data. So if I'm running a node, it is not super important for me when I'm importing blocks that I'm writing the data to the actual low-level database right away. The database can actually queue writes and wait to optimally write to my hard drive. In the situation where my computer crashes, guess what? I just start at whatever the last write was, and I synchronize the blockchain again, right? It's not so important for me that the data was actually written at the exact time. Now, we expose to the client synchronous write operations, right? We don't want the client to have to await for a write to happen, so we make the API easier. But again, you can imagine the database here is lazy. It's lazily writing data, and this is efficient because specifically for the blockchain context, we know the data will always be reaccessible if we want to. Does that make sense? This, again, the kinds of optimizations you can make when you build a blockchain first database. Not only the small data sizes, fast reads, but also lazy writing. This is why we built our own. So let's look at the practical benchmarks and considerations of building this database. Okay. What am I looking at here? So this is a table of data in the Polkadot runtime. So I think that this was from 2021, 2022. I don't remember what year, right? But this is like, you have a Polkadot blockchain running, and it accumulates data, and every single one of these dots is data in the database, right? What is the difference between the blue? So this is yeah, I don't know why I have blue and red here. Oh, blue and red is saying kind of how long it takes for RocksDB to read or write that data. But the more important thing I want to show you is this, that there is almost no, so 10 to the 3, that's 10 kilobytes, right? 10 to the 3. So this is 32 kilobytes approximately. There is basically no data here, right? So 32 kilobytes would go close to here. 10 to the 4 is 10,000. So this is 32 kilobytes, right? 10 to the 4, that's 10,000. 3 ticks from there. So this is 32 kilobytes. There is literally a handful of data points here, right? Most of the data is less than 32 kilobytes. And a ton of the data, again, you can't even see how dense this is. This is the density. The density is right here at the size of a hash. I think this is actually the size of an account. So in a blockchain, yeah, do I say that? Yeah, in a blockchain, majority of the nodes, the data, are just the account. So the account has the balance, has the nonce, has whatever. So that is that giant spike here. This is the size of a single account. But most of this data, there's only the WASM blob and a few special things that are bigger than 32 kilobytes. So all of the optimizations we designed work perfectly for all this data. Okay? Here's the same graph, but where the density increases opacity, right? So where you see here it's very light, the dots were there, but they're low opacity. Here where it's very thick, there's lots of dots there. Okay? Okay. RocksDB versus ParityDB performance, right? This speaks for itself. RocksDB is in orange, ParityDB is in blue. At every single point in this graph, ParityDB is more efficient at accessing data. Now what's interesting, look at these chunks. So here you have ParityDB kind of increasing in time to access, and then you have these steps. What's happening here? What is this line? 32 kilobytes. So we talked about it. So when you have a file that's bigger than 32 kilobytes, we chunk it, and therefore accessing it is slower. But it's still significantly faster than RocksDB. It's flat, yeah. Just turn it off, guys. Oh, okay. Anyway, so you can see ParityDB has a really measurable performance increase. We also found in benchmarking that RocksDB was super inefficient, was super inconsistent. So during the benchmarking process, we also found RocksDB had these giant spikes at random points. Again, these are all these configuration knobs where like things were looking good, but suddenly you get these giant spikes. I mean, this is time in milliseconds. So there were some reads that were, again, we were able to reproduce this over and over and over, where reading one item from the database took over a second. So RocksDB was totally crazy. It was not consistent. Alright, so things we tried, things we learned. So, isolating database benchmarks from the actual regular benchmarks. So what we tried to do initially when we did benchmarking was just benchmark the whole extrinsic, including database operations, all in one benchmark. Like we would try to include the time it takes for RocksDB to actually write the data. But because of this inconsistency, we just couldn't get consistent results with that end-to-end. So what we did instead was we separated the benchmarks. We have separate benchmarks for database, which are completely separate and do like a whole bunch of different things. And we have benchmarks for the extrinsics, where the database reads and writes happen in memory. So memory is very consistent. There was no problems. We got exactly perfect reproducible results. But it doesn't actually take into account the time it takes to do the low-level database reads. So we separate the two things out. We have in-memory with the computation, and we have the low-level database, and we combine the two, and that's the final extrinsic. That's why you have those two different pieces of the benchmarking pipeline. Okay? Fixing nonlinear events. So, when we executed a whole block, and we increased the number of transactions, we expected to get a linear growth of execution. What we actually got was something super linear. So when you were asking me, detecting it, I mean, maybe some software could have detected this, but truthfully, only by kind of analyzing our own data, we saw this super linear growth. So you see here, 500 transactions took 200 milliseconds, 1,000 was 500, 2,000 was 1,400. It was super linear. What we learned was, every time we appended a new event, we were passing this object back and forth from the WASM. So we created this append API, which I talked about, and look at this. Change, minus 95.52%. So there are some things, even an amazing engineering team, you only figure out after benchmarking, you know? You have to actually see how things are being worked. And now we have linear time and an append API. Weight refunds. So we tried to assign weights to all extrinsics for the absolute worst case scenario. But we found out that in many cases, we cannot know accurately what the actual weight will be, right? And that this worst case scenario was too pessimistic. So actually in PR, and I have PRs for all these different ones, so you can look them up, right? So that's cool. PR 5584, we introduced this weight refund. So I taught you how you can do a weight refund. That was something that we added after the fact, knowing that all of these weights were too pessimistic. Now we need to have pessimistic weights to be safe, but we can also create code which makes things better for the user, right? And I'm sure there's many more of these things we can create. But I want to mention to you, like, again, this is all about, just because it doesn't exist in Frame, like your ideas, doesn't mean it can't exist. That we had weights in our system for a while, Only later we added things that kind of make sense. It just takes programming, man. It just takes programming, design it, put it in. These are all opportunities. Every single time you guys have an idea for something better, we want to see the PR. Customizable weight. We used to hard code write the whole formula in the weight thing. We realized this is not scalable. This doesn't work. So we then figured out and turned it into a trait, and we generate a file, and this was the scalable way of doing it. So the way that we have it now, of having it all be in a file, it wasn't like that originally. It was literally hard-coded in. This is another improvement to the developer quality of life. This inherited weight call syntax, this is actually quite new. Like, this PR is 6,000, that PR is 5,000. This PR is 13,000. That only recently we made this thing where you can have one call weight at the top and pass the whole weight info, and it'll match it to every single function. So again, improvements to developer quality of life are still happening very recently, right? New ideas. Custom benchmark returns. So we noticed that there are times where a benchmark just can't be executed. For example, if you want to make, like, we talked about how you can have a configurable origin for different calls, right? What if you configure the origin so that no one can call it, right? Then the benchmark can't run. So you can write these fallbacks where basically, like, if the benchmark is returning an error or something, you can override and hard code whatever data you want, right? So you can choose what data you want to return back from the benchmarking pipeline. Again, it's not something that's often used, but is available to you. Negative y-intercept handling. This was a PR where basically we would do the linear fit, but then we would say that at 0 it's negative time. That obviously doesn't make any sense, right? You can't have a function with negative time. So we solved here the ability that 0 always has to intersect at least at 0, right? Can't go below. Multi-dimensional weight. This is, PR 12,000 something. We didn't add a second component of weights until pretty recently. And man, this was a crazy, annoying refactor. But eventually we did it, and it was important for parachains. And again, you can imagine that this can be extended in the future. And our APIs now are more flexible for extending it. Okay, finally, almost there. Best practices and common patterns. Your initial weight calculation must be lightweight, right? You cannot have a weight formula which depends on reading storage, depends on calculating complex functions. Your weight should be plus signs, minus signs, multiplication of scalar numbers, right? Because you need to know the user can pay that fee before you execute anything expensive. If you introduce high complexity logic to your weight function, you expose your runtime to be DOSed, basically, right? So, no storage reads, lightweight calculation. You can see here an example, the transfer, wait, what am I trying to do here? So the reason why no storage reads, you can see that doing a balanced transfer is about 50 microseconds. Doing a single storage read is 25 microseconds. So if you were to try to read something for the weight, you're basically doubling the weight of the whole call, right? Set bounds and assume the worst. So when you're building these weight functions, you need to have everything in your palette bounded, right? Any kind of high complexity function bounded with an upper limit. And then when you're doing benchmarking, you should always assume the worst case scenario. Again, there are ways for you to refund things in better cases, but you should always assume worst case scenario because that is the condition for which someone will attack your chain. Separate benchmarks per logical path, and we'll do this in the example. But it may not be clear. Like, it may be possible you write a benchmark with multiple different paths, and it may not be clear which path is the worst case. So what you'll do is actually write benchmarks for all the different paths, and then in your weight function you do the max. So you have formula A, max formula B, max formula C, and the weight of that function will be whatever the worst path will be. And you can imagine that I'm running a blockchain using your palette, and my blockchain is optimized for data read and write. And another blockchain is optimizing for execution. So it could be in blockchain A, path A is fastest. In blockchain B, path B is fastest, right? So having this kind of formulas that where you're doing the max It'll ensure safety across both blockchains. So you can do comparison operators in the weight definition. So that's what I said, basically. Path A, max path B, max path C. And this does show up some places of our blockchain. Keep extrinsic simple. So because of that exact reason that you have to do this pathing thing, it's better if your extrinsics have one input, one output, like one pathway through. The more complex your extrinsic is, the more difficult it is to do benchmarking and to do weights. So it's better to actually separate logical paths into small extrinsics and then use things like batch to combine them, right? So there was a comment earlier today. Why do I need to that you could design the API for the DEX, create pair, add liquidity. It could just be add liquidity, and if there's no pair, it creates the pair. Now, in this case, there's two logical paths. I recommend create pair as one simple path, add liquidity as one simple path, and if you want the user to click one button, you do batch. Right? This is better for weights, better for benchmarking. Yeah, that's exactly what I said. So simple, multiple extrinsics. Minimize the usage of onFinalize. So this is exactly what we talked about. That onFinalize is the last thing to happen in a block. It may be that after you run all your block, you still need to do this function no matter what. And it could be that it's less than what you have available. If you use onFinalize and you don't benchmark it correctly, you end up making blocks that are too big. And in a parachain, this will not import into Polkadot. Okay? So better to move things to oninitialize or the extrinsics, make things happen at the beginning. Yeah. One more time. So as we learned, oninitialize and onFinalize must execute every block. The logic of that code must execute. But onFinalize only starts executing at the very end of the block. It could be if we have bad weights, if we have bad logic, which I hope you don't have, that we fill up the block so that we only have this much available, but actually our onFinalize needs more. Okay? In this case, you've made a block which is too big. On a relay chain or on a solo chain, what that means is your blocks will be slow. You'll have blocks where instead of 6 seconds, it's 7 seconds, it's 8 seconds, right? That's not horrible, but it's not great. In Polkadot, the relay chain will reject your parachain block. It will not even allow you to be a little bit slow. It will reject it. So you will stop making blocks. So avoid using onFinalize. Move the logic to oninitialize.
Hi.
Yeah.
So I have seen parachains having block time of up to 25 seconds.
Yeah. That's not their fault. That's our fault.
Oh. Okay.
Most of the time. Most of the time. But that's our fault. But you know, we're building cutting edge technology. Things happen. Let's save it to the end. We're almost there. We're almost there, okay? Transition logic and weights to oninitialize. That's the whole idea, right? So move from onFinalize to oninitialize. You know, if something was going to happen at the end of the block, have it happen at the beginning of the next block. Understand the limitation of pallet hooks. As we talked about in the benchmarking, you can expose these hooks to your developers. They can write their own functions, but if they write really complex functions, your benchmarks aren't going to handle it correctly. So it's very good when you're exposing APIs and interfaces that you actually go ahead and define what you expect the complexity of that function to be. Keep hooks constant time if you can. And that's it. Questions? Okay. Why don't we put the mic back there?